Okay. So,
Am I in the way?
so one of the things
A little bit,
comes
both of
out
you are.
of deBroglie or
deBroglie.
comes out of the ability to scan and get images that are really clear and things that are really small. So here's kind of the rule is that if you want to see anything, that the wavelength of light that you want to look at it needs to be that size or smaller. So here's the catch-22, and this is how this relates to electrons. Everybody says, hey, well, let's look at an electron. Great. Let's look at an electron. So to see an electron, or for you to see anything, light has to hit and bounce off. So you're seeing me because light is being bounced off of my shirt. I'm seeing all of you because of the same process. So if you wanted to, quote, see an electron is extremely small. So to get a clearer picture, that would mean that you would need an extremely small wavelength of light. But here's the problem. Once you shrink the wavelength of light to a really small number, what happens to the frequency?
It goes up.
Frequency goes up. What happens to the energy?
Down.
It goes up. So to see an electron, quote, see an electron, you would have to have light of an extremely short wavelength, extremely high energy, and in the process of seeing it, it's like the photoelectric effect on steroids. You would give it so much energy that it would knock it out of its orbit, and then you wouldn't know where it was. So here's the analogy, okay? And we'll get into later on as what's known as the Heisenberg and cylinder principle. Is that if you're, imagine it's dark outside, and you're blindfolded, and you're trying to find a soccer ball that's rolling around somewhere on a field, okay? And your only methodology is to walk around and go like this blindfolded. Okay, so you're trying to kick and find the soccer ball, okay? And you know the soccer ball is going around somewhere in the field. So eventually, through random luck, you kick the soccer ball, and you go, great, found it. But by the act of finding it,
You lost it again.
you don't know what it is anymore, because now you've disturbed it. So the act of seeing the soccer ball disturbs the path of the soccer ball. So what comes out of this then is say, okay, well, if we want to see small things, light won't work. So let's use electrons. And this is the spin-off of the deBroglie equation. So if you look at the deBroglie equation, and that lambda equals h over mv. So you want a short, the smaller the wavelength is, the higher the resolution is. So if you look at calculations of this wavelength, why do you use electrons and not protons? Electrons have less mass, so you're dividing by a smaller number down here. Okay? Then, with the velocity, because on this one it says, on that first question, on question number 14, you've got to have the best resolution, you have an electron microscope, use very fast electrons or very slow electrons. Explain. So, here's the story. With that velocity, you want to shrink the wavelength. So do you want electrons that are moving fast or electrons that are moving slow?
Fast.
You want fast electrons because you shrink. So what this does, so here's some random pictures from so this is why I have nightmares about biology. So this is like you might like literally standing minding your bed, okay? extremely high resolution.
Wow.
Wormfly larva.
Bert, I did not need to know that.
Bert,
Don't we
that's
have
in
those
your
mites
head right
on us at
now.
all
I'm not
times?
stopping.
Like on our faces?
I didn't need to know that.
Like even after we shower and stuff?
So
What
this
is
is
that?
a bee
What is
antenna.
that?
Oh my God.
Wait, that's an Is that like
So
is that
blood cell in a mouse's lungs.
That's actually really cool.
I did not need to see this.
There's
It's a tardigrade.
yes, water bear.
You don't know about.
Why would you tell me to look?
What is the hardiest life form? Hardiest.
Cockroaches.
hardiest.
What is hardy?
It's
It's white blood cell attacking the
They
bacteria.
can like survive. They can survive being inside of a volcano, like being outside of the vacuum.
Kind of like a
No, literally.
That's just the leg of a fly. Larva head. That'll give you nightmares.
I'm not down to you up.
The inner structure of a fly's eye.
Yeah, there's like
There's two birds.
because you pissed me off.
Acorn
Gaslit
shell
me for
lining. Hydrothermal.
Whoa, bro.
That thing got
Skin of a scuttlefish.
Yo, that's really cool.
Bacteria that cause bubonic plague.
What?
Just very
Ooh,
bed bug. If you've ever had bed bugs.
Stop!
What?
Why don't you there's a spider in my toilet.
Hey, can we be done?
I see with spiders, bro.
That's kind of cool. There's a dandelion puffball.
That is not kind of right next
No, he was talking about this.
I'm not looking again.
That's a dandelion puffball.
Anyway,
Now he changed it. You didn't look. I told you to look.
Yeah.
He's slipping through the squeaky Shannon.
Good for you, Big Mike. Big Mike found a cricket.
Egg-laying apparatus of the fruit fly.
Ryan,
Wow.
if I was a spider, I'd sleep under my covers, bro. Like, you can't even lie, bro. Like, I ain't
Wait, just about like he says he's a kind of
Wait, Johns Hopkins.
Cancer by John Hopkins, researcher by George Gay. Yo, wait. Shit, look at that. That's a red blood cell.
And a lymph. Yeah, but like, what like
Yo,
shoot,
hey,
That's just horrible.
That's a wall.
Yo, Mara,
It's like a tumor.
It's just a wall.
Knock, look at that.
It's kind of disturbed. It's a little disturbed.
Hey, Bert, do you think my CeraVe salicylic acid solution will get this?
Microscopic organisms in a fossil record that spans 500 million years. Each form is just a single cell, but yet they grow complex cells around themselves from seawater minerals and accumulate layers of sediment.
That's kind of
I don't know
cool.
what that is, but it's weird.
Single cell. Oh, MRSA, hell no.
Either of these square. Oh,
This is where the eye puts the skin on a European bee.
They just add that in for fun.
Nanoflower.
So you can like compare
Yo.
Heavily infected with SARS-CoV-2. Grain pollen.
I hate
What?
pollen.
That's kind of cool.
I hate pollen.
I want them to zoom in on that one more.
Just pay attention.
High
Now you're
magnification
paying
on
attention.
pollen inside the cavity where pollen is stored in flowers. It
Not
looks
even
like
you're paying
eggs.
attention.
Yeah, because I have an A in the class.
Okay.
You have an A?
More pollen.
You gotta wait tiny, bro. It's not
Wait, don't you have like an 81
Oh, profile of a moth.
Dude, I thought we were a C.
That's really cool, actually.
It
I thought
is.
we
It
can
actually is
generate
cool.
it.
Like the
So
proboscis.
whatever it's called.
Tobuscus?
Like the YouTuber?
Burkamp, you're showing us biology right now.
I know.
And it's better than
Hey, no, not the last
See, there's a salt crystal.
Like, Shan,
We're back to
look.
organic.
Yo, that's a salt crystal.
It looks like it over the
Hey,
side.
Flower. That looks like something out of Star Wars.
Yo, why is that?
It looks like something from
Why is
Pizza.
that looking tough?
Huh?
Why is that tough?
Size what?
So
Why is
how many
that
they
different?
own Adam and Digital?
Why is it what?
No, don't worry about it. Don't worry about it. Don't worry about it.
Okay. It looks like someone from
Alright. So, enough of that. So let's talk about question 17.
Thank you.
Thanks, Ethan.
So electrons are accelerated from rest at 8,000 volts, right? By what factor does their deBroglie wavelength increase if they were instead accelerated through a 2,000 volt potential? Okay? So here's the story. So what fundamentally you're going to be talking about wavelength, right? Okay. So cool with that. So if you look at that wavelength between H over MV, basic equation for the deBroglie wavelength. So this is where I went through yesterday and said, okay, you can also look at this as H over M times the square root of 2K over M. Okay, so this is that kind of that shell game that I played where you can substitute kinetic energy in for velocity. So if you take kinetic energy, okay, 1/2 mv squared, and you solve this for velocity, okay, you get the 2k over m. You take that and you put that in for v. So this isn't anything radical. This isn't weird. Okay, all I did was substitute that in. Okay, that's all I did. I just took, and it's a simple substitution. Now, you're looking at this as a ratio, okay? So, you're going to look at the H over the 2,000, and let's just think of this through.
2,000?
Which one's going to be accelerated more? The electron going through the 8,000 or the one going through the 2,000?
8,000, I think.
8,001 is going to accelerate more because there's a bigger voltage difference, right? Okay? So the bigger the voltage difference is, the more it's going to get accelerated. So all I'm going to do is just look at this as a ratio. Okay? So I'm going to look at this in terms of a whole bunch of things that are going to be the same. So you've got the masses are going to be the same because it's an electron in both cases, right? So if you set this up as a ratio, the electron's mass is going to stay the same. So that's not really even a factor, right? So those I'm not even going to worry about. So here's the story. If you're going to look at this as a ratio, and you have H, which is a constant, which is also a ratio. So if you look at this, the H's are all going to cancel out because it's the same Planck's constant for each one of them. You have the masses, which are going to be the same, because you're comparing electrons to electrons. So you really don't even have to worry about that. So what's the only thing that's underneath the radical that you're going to worry about?
The 2,000 and 8,000.
The 2,000 and the 8,000, because that's going to determine the kinetic energy. Okay? So basically, if you look at everything that's going to stay the constant, so because it's the voltage that's going to determine the kinetic energy. So, and that's underneath the radical. So if you look at the square root of 8,000 volts over the square root of 2,000 volts, at the end of the day, you're taking the square root of
4. Which is 2.
which is 2.
Oh, I got 2x.
Yeah, I got 2x.
Attaboy.
Really, big mind. Not 4. You did
Hey,
4.
Shaq, hey, Shaq. Look up and down the board with the cardboard. Square root of 4 is 2.
Force equals MA, bro, so it's gotta be 4. Oh wait, it's not velocity?
What is this faded number right here, Michael? It looks like a really
Shaq.
Why are you
Alright,
throwing things?
even about
Why are you throwing things?
I think
Why are you throwing things?
Number
I
8
do.
on
Why?
problem 18.
I want to get that in your hair.
Okay?
Terrible GPA.
Yeah.
Oh yeah, horrible GPA in electron volts.
And we round up on 18B.
On 18B, you round up. So your answer to 18A is that in electron volts is a horrible GPA. Okay?
Hold on.
We're dogging on
Hold on.
Hold on.
What if it's a horrible GPA times 10 to the third?
Oh.
Talking about big money.
10 to the third. That's a great.
How many electron
That's
volts
like
do you
that's
have
a great
on-
perfect GPA.
On 20 in nanometers.
And then.
Do they all have a 413?
They all start with a 4.
Oh, it's
You think
because.
progressive
Yeah.
Yeah, it's just your. It's your
Really?
So how do you do
Because
it?
you take your instrumentation A
Yo.
divided by 1.
Hey, you want to see? Hey, it's HC over
wavelength.
wavelength.
Yes.
No, that's H.
You should have gotten a number less than 1,204.
HC.
It is hell.
Yep.
You should have.
Yeah.
You're dividing,
That-
Michael. Wow.
He has rights.
No, you did, Michael. You couldn't have gotten something bigger than 1,204.
On 30, with the kinetic energy and electron volts, you've got that, and then you want to, yeah, I don't know what it is. So on 30, when you calculate the velocities, that would make a decent, pretty decent GPA times 10 to the 6th. Right? And your answer to 30 is B, because that's a proton and that has more mass.
Great music.
What?
Hey, I agree with him. Great.
1990. Oh!
No, it's the one book.
Red Hot Chili Peppers.
So the answer to 30B should be around 2,000.
Oh,
let's not stop giving spoilers out, bro.
Oh,
Almost nothing does the whole
Red
time.
Hot Chili Peppers. Hey, I don't know.
Mr. Burkamp, we just give it 34. Cut to the chase.
Hey, can I
Okay.
something?
Yeah,
Let's not act like we knew how to do 34, okay?
Holy Lord, bro, then you did not. You did it,
How
bro.
about
You get 44.
So on 34,
AI.
Hey, focus, please.
What in the world?
you need this little bit.
Mr. Burkamp, did you tell us that yesterday?
I did not. That's why we're going over it right now.
Okay,
Hey,
thank
Michael,
you.
how do you figure you needed that much? What?
So-
This is the first time I forgot something.
34.
Okay, so what this gives you is the kinetic energy of an individual particle, okay, or gas, whatever it is. So here's what's important. This is what's known as Boltzmann's constant, which is it's on your sheet, it's 1.38 times 10 to the minus 23rd joules per Kelvin, okay? So on 34, what you've got to figure out is that it's 0.1 microkelvin. This is not absolute zero, but it's really, 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 really close to it, okay? And the only way you can get it this, quote, cold, and by cold we mean a lack of entropy or a lack of movement, is to basically lock it into a laser trap where it basically can't move. So you're holding it trapped in a series of lasers that are all intersecting, and therefore it can't move.
The constant K is what?
So the big K is Boltzmann's
It's right here.
constant. The T is going to be temperature in Kelvin.
Okay.
So here's the significance of this equation. What this means is that the kinetic energy of a gas particle, whether it's carbon dioxide, nitrogen, oxygen, whatever, is only dependent upon the temperature. It's not dependent upon the mass. It's only dependent upon the temperature. And this should make sense. So as you warm things up, they have more and more kinetic energy. But here's your trade-off, though. The kinetic energy is the same. So if you have a hydrogen molecule and you have a big, massive carbon dioxide molecule, both at the same temperature, they're both going to have the same kinetic energy. But here's your trade-off. Kinetic energy is 1/2 mv squared. So what that means is that the hydrogen has a very small mass. So therefore, it has to be moving much faster. The carbon dioxide relative to the hydrogen is much more massive. So it's going to be moving slower. Okay? So particles at the same temperature of gas have the same kinetic energy, but that doesn't mean they have the same velocity, okay? But they have the same kinetic energy. So what you have to do on 34 is find that kinetic energy. Then, this is one of the equations we came up with yesterday. Then you can go, oh, energy is momentum squared over 2m. Okay?
Well, we have to drive that, or would you give that to us on test if we need it?
It's just handy to know how about that.
Okay.
Now, here's the problem. So, you found the value of the kinetic energy, which is a horrible GPA times 10 to the minus 30. Okay? But you also need the mass of the particle. So, because of the fact that you're talking about on the rubidium atom, so there's some things you need to do. You need to find the mass of, the molar mass of rubidium. Okay? So once you get that, then you can figure out that's 1 mole of it. So then, if you know the mass of 1 mole, you can divide that by Avogadro's number and find the mass of an individual particle. Yes?
Can we get an estimate on the answers?
So the overall answer on 34 for that wavelength should be around 900 nanometers.
900? Oh, okay.
Nanometers.
Ryan, you good, bro?
Wait, what if I got 27.3? 2.73 times 10 to the negative 8.
No, that's horrible.
Oh, really?
Of the diameter of the
No,
atom.
you need to divide that by.
Huh?
Avocado.
Of the diameter, yeah.
So the mass of an individual rubidium atom is something times 10 to the negative 25th.
Yes.
So if that number is wrong, kind of what you're doing is going to go bad. So
How did you get that?
Why is your TV glitching?
I don't trust you guys anymore. You don't need me.
Everyone's so easy.
That is not, wait, that's your joules? That is not correct.
Wait, Bertram, what if, is it okay if some of our answers are in like
Oh, I
joules
didn't do
instead of like the electrical thing?
like which one?
No, it's the negative 23rd.
Like the 17 problem?
Yeah,
I
1.38
don't know,
times
some
10
of
to the
them
negative
didn't
23rd.
specify.
I've got my answer. My answer sheet has both of them.
And then
Okay.
0.1 times 10 to the negative 6.
So on 34,
And then times 3.
here's kind of the order of magnitude. You can find that momentum, then
Yeah,
once
so
you
that's
get the
not what you
momentum,
have.
then you can find the wavelength. So the energy from that equation of Boltzmann constant should be 10 to the negative 30. The mass of a single rubidium atom is 10 to the negative 25th. So your momentum is going to be a really, 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 really small number.
We're not even.
Big Mike,
I want to find for mass. Do I just take the molar mass?
Are we really on a
rubidium over
Yeah,
Avogadro's
yeah.
number?
but that's in grams.
Yeah.
Kilogram.
Tell me. Oh my god.
Oh my god.
Ah.
My bad. I should have stressed the importance of the MKS system earlier.
But that was like a year ago. I'm a changed man.
Wait, what did you do it? How did you do it?
10 to the negative 25.
So then
Wait, so
we
it's
take our
right
H
times 10 to the
value.
negative
Big Mike.
Oh no.
Big Mike. What was your answer in?
6 times 10 to the negative
I'm
30.
just giving
So it's
you
a
the order
3,000.
of magnitude.
Big Mike, close it in.
Around
Wait, how do you find the math?
Big Mike.
Mole.
Better not be lying.
You use the mole.
Big Mike.
And then divide that by
8?
Nathan. What was Big Mike's answer in?
5.
Hold on.
What's the
No questions
molar
asked.
mass of
What was it?
rubidium?
Just tell me.
85.47 grams.
85.47.
You didn't get 8
grams per 6.02 times 10⁻².
Kill me right now.
atoms. So then you can find the mass of one atom that's in grams.
What do I do after I find momentum?
You need it in kilograms.
Yeah, that was my problem.
Hey, just
My bad again.
Hey, Big Mike, just divide it by 2.205. Ain't that right, Barry?
What?
Just divide it by 2.205.
Why?
If it's in pounds.
What?
I thought he did it in pounds. Okay.
You're not looking. You're writing stuff in my. Let me get this.
Or just divide it by 1,000, bro.
You're bullying me.
Okay, Wyatt, your answer was right.
865? You might be.
Hey, that's what I got.
Dude, I just want someone.
Hey, I'm not reading it. That's
What do you mean you don't know?
Shaq, I said the answer was around 900.
She's sick.
Nathan,
Do you want to say hi?
But yeah.
Do you want to say hi?
Okay.
Mr.
I love you.
What?
What'd you get?
Wait, what if we
That's
just-
why I got
He wanted to say hi to Popcorn.
Yeah, I know that.
All right. Anything else?
Yeah, I didn't. Mr. Burkamp, what should our
Big Mike.
on 34.
Yeah, I did.
You said the answer was around 900, but for the other part, how many like times what?
Around 3,000 to 4,000.
Mr. Burkamp?
I got 100 times.
What?
Our momentum, what should it be?
On which one?
34.
The momentum itself
Yeah.
should be 10 to the negative 28.
Okay, so you take H over that. Yeah, just give me your weight, bro.
Yeah, that's right.
But that's going to get you an answer.
Still.
But,
That's
and I
why-
just
that's
did
why I'm
the
gonna fail
answer.
this.
I
I mean, everyone's
I'm still getting
the effort is correct.
When you get 1.3,
No, I have 1.22.
what is H? Isn't it 6.63?
Well, you said it's around 800.
H is-
900.
something to the
Oh, good. No, I know it's the negative 20.
What did you give your P?
Oh my God.
I'm tempted.
Oh.
I got it now. What you I don't know. Newton meter.
New seconds, bro.
Okay.
No, I didn't. It's literally like.
Yeah, give me a second.
Anything else?
This math sounds
Once, twice, sold.
Oh, wait,
All right, stop that camera, please.